Hey, hello everyone. My name is Surena Hozoori, and I'm very happy to talk about my results in nearly carbon neutral geometric topology conference. I want to thank the organizers for that. And today I want to say a few words about contact and symplectic topology on one hand and Anosov dynamics on the other hand. These are both theories that they have quite interesting and deep relation to the topology of the underlying manifold, and my goal today is to explore some connections between the two theories. So I'm going to present my work in two parts, in two talks, basically. In the first talk, which is this one, I'm going to talk about, give you like the necessary background for understanding the main result. I give you some background in contact and symplectic topology, also some background in Anosov dynamics. And in the second talk, I will talk about the main result, a little bit about the proof and some consequences. So to put things in to give some historical context, Anosov flows were introduced by Anosov in early 60s as a generalization of the geodesic flows of hyperbolic manifolds. Immediately, many interesting global properties were detected for this class of dynamics, which made them kind of the center of attention at the time. Primarily, tools of dynamical systems like ergodic theory were used to explore these global and like rigidity type of results for these flows. If you look at the literature, you'll see many big names like Margulis, Ismail, Pugh, and so on. But more profound relations, deeper connections to topology were introduced thanks to the use of foliation theory in dimension 3. This was started by Thurston, Plante, and Berjovsky, but more modern techniques were introduced in mid-90s thanks to the works of like Sergio Finley, Barbaud, and their co-authors. A few times I mentioned that this class of dynamics, they satisfy interesting global properties. So let me give you a few examples of such properties. For instance, Thurston and Plante, they showed that the fundamental group of the underlying manifold admitting such a like flow should have exponential growth. If you don't know what exponential growth is, that's fine. That basically means that the fundamental group should be very, very large. And that automatically excludes manifolds like the sphere, the torus, and Niels manifolds from admitting any Anosov flow. Another, I think, interesting global property for these flows is that they don't have any contractible orbit. And another classification type of result is due to Gis and independently by Barbaud. They showed that on ciphered fibered manifolds, Anosov flows are up to a finite cover orbit equivalent to geodesic flows, which basically means that on ciphered fibered manifolds, we have a very nice classification result. So notice that the first and the third results, they tell you that a lot of the mystery about Anosov flows remain for the case of hyperbolic manifolds. So my goal today is to give you a contact and symplectic geometric characterization of such flows in dimension 3 and use this characterization to set up a framework to use all the tools that we have in contact and symplectic geometry in the study of questions in Anosov dynamics. I should mention that the connections to contact and symplectic geometry were observed by Mitsumatsu and independently by Eliashberg and Thurston in mid-90s, but I will use some geometric quantities named growth rates and some careful geometric approximation techniques to turn these observations into a full characterization. So during this talk, let M be a closed-oriented connected free manifold, X a C1 non-vanishing vector field on M, and phi of T the flow generated by X. So I want to go give you some elementary notions in Anosov dynamics to make sure we're all on the right foot. So we call a flow Anosov if there exists a splitting of the tangent space Tm into 3 line bundles. One is ESS, EUU, and the direction of X, which is the direction of the flow, such that, first of all, this splitting is continuous and invariant under the flow. And also, if you look at the action of this flow on a vector, let's say in the EUU direction, the length of that, the push forward of that vector under the flow will be growing exponentially. And if you take a vector in ESS direction and look at like what happens when you push forward it along the flow, the length of the resulting, this push forward will be decreasing exponentially. So in this definition, A and C, they're positive constants, and you're also dealing with a norm, which is induced from some Riemannian metric on the tangent space. In general, it's just a C0 Riemannian metric. And I should say that we call these two line bundles, EUU and ESS, the strong, stable, unstable, and stable directions respectively. And this is the picture that basically summarizes the previous definition visually. Like, so if you look at what's happening on the ES direction, you have like this contracting behavior. If you look at what's happening in the EU direction, you have like expanding behavior, and that basically determines what's happening to the rest of the tangent space. A few remarks that they're kind of like technical, but I'm going to use them later on. So notice that although the metric in the definition was C0, you can always integrate this metric along the flow and basically get some sort of average of this metric. And after doing that, first of all, you can assume that A in the previous definition is 1. So what was A? A was this constant here. When we say we can assume that A is 1, that means that we can assume that the exponential growth and exponential decay, they start immediately. And also I can assume that the metric that I'm dealing with is differentiable, at least in the direction of the flow after doing this integration. These are quite technical, but they're kind of important for me. And also another important result is that you can easily see that if you pair, let's say, ESS direction with the direction of the flow, or the EUU direction with the direction of the flow, you will get integrable plane fields. But what you don't immediately get, and it's true, is that these are uniquely integrable plane fields. And that basically gives you that C0 foliations with C1 leaves. And I should say that we call this foliation, again, stable and unstable foliations. And that is really like the reason why, how people like use, foliation theory in the study of Anosov dynamics. So a few examples of these flows. The first two are like the most kind of classical examples. One of them is a suspension of an Anosov diffeomorphism of two torus. We can easily see that that's an Anosov flow, which is on a torus bundle. And also, as I mentioned, geodesic flows on the unit tangent space of a hyperbolic surface. That's also going to be an Anosov flow on a 3 manifold. And it's important that she showed that these are actually the only examples if you assume that the foliations that I discussed are smooth, which also suggests that a lot of times we're dealing with foliations we really don't have regularity, and it's really hard to control the regularity of the splitting or even the foliations, even if when the flow is like C infinity itself. But for now, by now, we know that, thanks to the works of Fulan and Hasselblad, we know that we have infinitely many examples on hyperbolic manifolds. So we know that these flows are not really that rare neither. So for various reasons, people were looking at the generalizations of these flows. I think one of the reasons is that at the time it was a motivating question in dynamics to try to, find some sort of global model for dynamics. So because of all of these rigidities and the fact that many manifolds don't even admit any Anosov flows, it was soon very clear that these flows, they can't be a kind of model for a generic dynamics. So people were looking at generalizations, and one of these generalizations is going to be the one which is going to be the bridge between Anosov dynamics and contact and symplectic topology. So in order to talk about that specific generalizations, I want to give you a few definitions. So notice that when you have a flow, basically any flow generated by a non-vanishing vector field, this will induce a flow on the normal bundle of the tangent space, via this projection that you have from Tm to this normal bundle of X. And we call this the Poincare linear flow. When the flow is Anosov, there exists naturally you can guess that, okay, this normal bundle has a hyperbolic splitting, in the sense that, again, you can split this normal bundle into an ES and EU directions, such that this is, again, continuous and invariant under this Poincare linear flow, and you have expanding behavior in EU direction and contracting behavior in ES direction. That's obvious because you're just killing the X direction from the previous, the splitting that you have in the Anosov case. But the inverse is also true, in the sense that if you have such a splitting of this normal bundle, you automatically can be sure that the flow is Anosov. So this is an if and only if statement. So why is that not trivial? The reason it's not trivial is that when you have a splitting and invariant splitting of the normal bundle, you basically have two like invariant plane fields in the tangent space, right? But in order to have this the splitting that you had in the definition of Anosov flows, you need two invariant line bundles inside these two plane fields. And that is not trivial, and it needs a little bit of work, but it's a very classical fact in dynamics that in the Anosov case, you can always just detect anosovity from looking at this, the induced flow on the normal bundle. So I'm ready to give you like the definition of that generalization that I'm interested in. So now we call a flow projectively Anosov if the induced flow on this normal bundle admits what we call a dominated splitting. So that is, again, splitting of this normal bundle into two directions, ES and EU, such that, again, the splitting is continuous and invariant under the flow, and you have relative exponential growth for vectors in these two directions, in the sense that if you take a vector in EU direction and take another vector in ES direction, just again look at the action of the flow on these two vectors or push forward them along the flow, the ratio of the length of these two vectors will be growing exponentially as you push forward them, right? So obviously when the flow is Anosov, you have this case, because in that case, the one in the unstable direction is growing exponentially, the one in the stable direction is decaying exponentially, so their ratio will be obviously growing exponentially. But it's not trivial whether it's not trivial how larger like this class of flows are, but I can just kind of spoil it for you and say that these are way more abundant than Anosov flows. Here again, A and C are positive numbers and you're dealing with some norm. So in order to give you a picture that summarizes the dynamics in this case, you should look at this picture. This is really what's happening. So if you think of this, this ratio, you can think of it basically as the tangent of the bisector of these two directions, right? You have an angle. Look at this bisector. It has some angle with ES direction. If the tangent of that angle will be basically just this ratio, right? Which is kind of splitting that vector into one into the ES direction and another one in EU direction. And this is telling you that the tangent of this angle is growing exponentially, which means that the action of the flow on this bisector would be pushing these bisectors towards the EU direction. Obviously, that's happening if you, in the Anosov case, if you remember that picture. But here is like the picture that just tells you about like the projective anosovity, pushing these bisectors towards the unstable direction. If that's what the flow does to these bisectors, that means that your flow is projectively Anosov. The corresponding plane fields, I should say, in this tangent space, they're integrable plane fields again, but they're not necessarily uniquely integrable, which means that using foliation theory in this case is quite more challenging. And I should say that the splitting, we know that we can't necessarily lift it to the tangent space, unlike the Anosov flow. As I mentioned, projectively Anosov flows are abundant. The first examples were given on the torus and Niels manifolds. Now we have non-Anosov examples on hyperbolic manifolds, and even better than that, Asaoka, Dufresne, and Noda, they showed that we have many what we call over-twisted examples as well, which is the term that I will explain later on. But in particular, we have infinitely many distinct examples even on the sphere. So let's get back to the, so the connection to contact topology is thanks to this quite elementary proposition, which tells you that a flow is projectively Anosov if and only if the direction of the flow lies in the intersection of a pair of positive and negative contact structures C plus and C minus. So I'm not going to assume that you guys know much about contact and symplectic topology. So I will go through a few definitions in the remaining time. So and I will get back to this proposition again, just to convince you that this is not really that complicated. That's why it's not even called a theorem. So we call a one form alpha a contact form on M if alpha wedge d alpha, which is a 3 form, is positive. Is non-vanishing. If it's positive with respect to the orientation, it's a positive contact form. Otherwise, a negative contact form. We call the kernel of such one form a contact structure. Again, a positive or negative contact structure. And the pair M and C is called a contact manifold. Whenever I don't mention anything, we assume that the contact structure is positive, unless stated. And notice that by Frobenius theorem, that means that C, or this contact structure, is a maximally non-integrable plane field. So in some sense, contact structures are the polar opposites to the foliations. Foliations are everywhere integrable, contact structures are nowhere integrable. If I want to give you an example, I can easily write a one form on R3. It's called a standard contact form. It's dz minus y dx. And we can easily write down the kernel of this one form and check that, okay, alpha wedge d alpha is just a standard volume form on R3. So this is a contact form. And the kernel can be, you can find the basis for the kernel as well. So rhond y and also rhond x plus y, rhond z, they give you a basis for the this contact structure. Here you can see a picture of this on at the origin. You get, you get a horizontal plane field. Notice that the y direction is always in the kernel. So that means that the y direction is always going to be tangent to the contact structure, but the other one will be tilting as you move along y direction, which means that as you move along y direction, the whole plane will be kind of rotating in some sense. And this is obviously invariant in x and z direction. So this will be the picture that you get everywhere. So you might say that, okay, this is just one example, but thanks to Darboux theorem that we know that all contact structures, they locally look the same. So this is an honest picture locally, and you can think of contact structures as kind of rotating plane fields if you want to have a little bit of intuition. And I should also say that Gray's theorem tells you that homotopy of contact structures can be done through the isotopy of the ambient manifold. These two theorems together, they basically tell you that there's no local theory for contact structures because locally they all look the same. And if there's anything interesting about them, is more of a topological nature. Let me give you a few more examples. On S3, for instance, consider S3 as the unit sphere in C2. The unique complex tangent line for S3, you can easily see that it's just a contact structure on S3. But I can also give you infinitely many examples on torus via this example. So if Cn is just a kernel of cosine of 2 pi n z dx minus sine of 2 pi n z dy, you can easily check that for when n is positive, this is a positive contact structure. When n is negative, it's a negative contact structure. And here you see that the z direction is always in the kernel. And if you think of T3 as, just this unit box with identified faces, this contact structure would be the one which these plane fields will be rotating n times as you go from bottom to the top part. In this picture, you see the case for when n is equal to 1. So getting back to projectively Anosov flows, the point is that, again, let me read it. A flow is projectively Anosov if and only if it's in the intersection of a pair of positive and negative contact structures. So notice that this is an if and only if statement, which is important for me. And how can you see that? You will see that, you can easily see that the behavior of these bisectors, which I mentioned, rotating towards the unstable direction, this is exactly the rotation that we had in the definition of contact structures. It's easy to prove that. You need it's very easy to prove that, but it's basically Frobenius theorem. So if you have a little intuition about Frobenius theorem, this is quite more or less this should be obvious. So if I want to give you non-Anosov examples, you can look at a horizontal foliation of torus by kernel of dz. You can easily perturb this into a pair of positive and negative contact structures, and controlling the angle of these contact structures, the angle it makes with this kernel of dz, you can make sure that these two contact structures are transverse. So, and you know that this is not an Anosov flow because there's no Anosov flow on torus at all. And we call this pair C minus and C plus a supporting bicontact structure for this projectively Anosov flow. A natural question would be that, okay, if I have a purely contact geometric understanding of projectively Anosov flows, is there some sort of contact geometric enrichment of these flows of a bicontact structure that makes it equivalent to an Anosov flow? And the purpose of my main theorem is to give an affirmative answer to this question. But in order to tell you about that enrichment, I should tell you a few more words about like contact topology. So going towards topology, I should mention that not all contact structures are equally important for topologists neither. A very important dichotomy is over twisted versus tight. We call a contact manifold over twisted if it contains an embedded disk which is tangent to the contact structure along the boundary. Otherwise, we call it tight. So this is the example of such a disk. You see that it's tangent to the contact structure along the boundary. And a priori, there's no reason for you to believe that this is an important dichotomy if it's the first time you see it. But the importance is thanks to the very celebrated theorem of Eliashberg, which tells you that over twisted contact structures up to isotopy are in one-to-one correspondence with plane fields up to homotopy, which basically means that all, you can, the information that over twisted contact structures have about the topology of the underlying manifold is not really more than the information that they have as plane fields. So in some sense, contact geometry is redundant for over twisted contact structures, at least their relation to topology. On the other hand, tight contact structures are more interesting. They're rare. Classifying them is way harder. And when they exist, they reveal more interesting connections to topology. And all examples I gave you, explicit examples I gave you, they were tight, but they all admit over twisted structures as well. And we can easily write down an example as I did here. One way to study this important tightness property is through four-dimensional symplectic geometry. And that is thanks to this theorem of like Gromov and Eliashberg, which tells you that if a contact manifold is what we call a symplectically fillable, then it is tight. So if I want to give you like few words about this notion, I don't have time to talk much about like symplectic geometry, but remember that a two-form omega on a four manifold is a symplectic structure. If omega wedge omega is positive, the pair is called a symplectic manifold. This is basically an even dimensional sibling of contact geometry. And again, you can write down a standard symplectic structure on R4 as well. And again, you have this Darboux type of theorem, which tells you that all symplectic structures are locally similar. And we call a contact manifold, in order to tell you about like this symplectic fillability condition, we call, assume that you have a four manifold, for symplectic four manifold, such that first of all, your contact structure is the boundary of the four manifold and all the orientations you have, they agree. And then we call this four manifold an exact symplectic filling for the contact structure if omega can be written, the symplectic structure on Y can be written as D of some alpha, where alpha is some extension of a contact form of C. So this is a little bit stronger than just symplectic fillability, but that's the notion that I'll be dealing with in my talk. So that's more or less enough for me. We call such extension of this contact form inside this four manifold a Liouville form. So notice that we call this exact symplectic filling because this is a special case when the symplectic structure you have is an exact symplectic structure. And as I mentioned, there are weaker notions of symplectic fillability, but even like the weakest one is enough for the tightness of C. That gives you a hierarchy of contact manifolds. On one hand, you have a general contact manifold, a subset would be tight contact manifolds, and you have this hierarchy of symplectic fillability conditions that understand that you can have on a contact structure. This gives you an important hierarchy in contact topology. Although it's not trivial, we can see that all these inclusions are proper. For instance, the unit ball in R4 with the standard symplectic structure I wrote down is an exact symplectic filling for the contact structure on S3. And also for the examples on the torus, you can see when n is equal to 1, it's exactly symplectic fillable. Otherwise, it's just weakly symplectically fillable. So to finish, remember that I said that projectively Anosov flows are in some sense equivalent to some contact geometric structure, which was called a bicontact structure. And the question was that, is there any contact symplectic geometric equivalent for Anosov flows, which is an improvement of projective anosovity? And my main theorem, which will give an affirmative answer to this question, and we'll build this contact and symplectic characterization, which is what I will be talking in my second talk. Thank you for listening.